So the last topic for this week is called power, and then you can start your problem set. So first of all, what is power? Power is the rate at which work is done, or the rate at which energy is transformed with respect to time. So in the past few weeks, we've calculated work, and we've calculated energies of different kinds. And so if we did a certain amount of work, if we divide it by how much time it took to do that work, then we get this new quantity called power. So it's basically how fast you're accomplishing that work. Or since work and energy are both measured in joules, you can do the same thing for energy. You can take, you can transform energy. So delta E stands for the change of energy. Divided by how much time it took to change that kind of energy. And then that's called the power of the energy transformation. The units for this, so first of all, the numerator is in joules, and the denominator time is in seconds. Those are the SI units. So we can say the units for power are joules per second. And we gave that another name. And that other name is called a watt, named after a scientist or engineer whose last name was Watt. So that's a capital W. Those are the SI units of power. So 1 watt equals to 1 joule per second. So I decided to calculate my own power of me trying to run up a set of stairs. Okay, so I ran up these stairs as fast as I could. I timed myself. This is the stopwatch. It took me 2.73 seconds. I measured the height of each step, which I got 18 centimeters. And I multiplied that by how many steps there were, 16 steps, giving me 2.9 meters in total, that I increased my height. Okay, so my delta H, my change of height, was 2.9 meters. And I also measured my mass. In kilograms, it's 70.7 kilograms. So to calculate my power running up the stairs, so since I'm climbing stairs, I'm getting higher. That means I'm changing my gravitational potential energy. So I did power equals my change of energy divided by the time. But more specifically, it's my change in gravitational potential energy divided by time. And to calculate gravitational potential energy, it's mgh. It's a delta H here because I'm calculating my change in gravitational potential energy. And I just filled in the values. I filled in the values that I measured. I calculated all that out in the calculator, and it turned out to be 736 watts, but that needs to be in 2 sig figs, so I just underlined the 2 sig figs there. All right, so that's an example of a calculation of power, and I did this one in terms of energy divided by time. Later on in this video, there'll be one based on work divided by time. So I ran up these stairs as fast as I could. I got 736 watts. Is that good? Is that a high power or is that a low power? This term came about horsepower. You may have heard the word horsepower before. And car engines are often described in terms of horsepower. And 1 horsepower is equivalent to 745 watts. So you'll see that me running up the stairs, I was pretty close to 1 horsepower. Why do they call it a horsepower? Does it have anything to do with horses? Yes, it does actually. 1 horsepower is approximately the power that a horse can, this is not grammatically correct here. 1 horsepower is approximately how much power a horse can do for an extended period of time. And this term was invented by James Watt, and that was in the late 1700s. So with breeding and all that, horses might be more powerful now. But back then, that was the approximate power that a horse could do for an extended period of time, like all day, because horses would work all day, plowing and doing all sorts of other work for humans. So I got close to 1 horsepower. Does that mean I'm as powerful as a horse is? No, definitely not. Okay. My 736 watts, I could not sustain that for an extended period of time. Okay. I only ran that for 2.73 seconds. And I mean, I probably could have did that for a little bit longer, but not that long. Okay. I definitely could not do that all day. This is the power that a horse could do all day long without getting too tired. A horse could probably, like if they were pulling their hardest, running their fastest, they could probably get like 15 horsepower or so. And then a car engine, I looked up one for a Toyota Corolla. A car engine's about like 140 to 170 horsepower for that kind of a car. This Camaro here probably has even higher power than that. All right, so that was kind of a diversion there, just telling the story about a horsepower. So now I'll show a second example of calculating power. Power is related to speed. So obviously how fast I was able to get up those stairs had a big influence on how much power I calculate. The faster I can climb the stairs, the higher the power is. So here's another question where I'm given a velocity. So let's just read it first. Kenzie pushes a heavy box with a force of 300 newtons forward, sliding it across the floor at a constant velocity of 2 meters per second forward. With what power is Kenzie pushing the box? Okay, so out of the 2 formulas to choose from for power, work divided by time or energy divided by time, I've chosen to use the work divided by time one because this sounds like Kenzie's doing work on the box. Okay, she's applying a force, 300 newtons, in the box, and it's making the box move. So I'll do power equals work over time. But I'm not given either of these two. They don't tell me the work. They don't tell me the time. Okay, they tell me the force, and they tell me the velocity. So what can I do here? Well, I can change work to the formula for work. Right? Work is force times displacement times cosine of theta. So I've changed work to force times displacement. What about the cosine of theta? Well, in this situation, the force and the velocity are in the exact same direction, forward. So theta is 0 degrees. So it's cosine of 0 degrees, which is equals to 1. And that's not going to affect anything if you multiply by 1. Okay, so just replace work with the work formula. So that gets me a force term here. So I can plug in 300 newtons for the force here. But what about displacement and time? Well, I don't know the displacement and I don't know the time, but recall that displacement divided by time is velocity. Displacement divided by time is velocity. So I can rewrite this formula as force times velocity. And now I can plug in the 2 meters per second for velocity. So it's 300 times 2, and that's 600 watts to 2 significant figures. All right, so that's the concept of power. Power is either work divided by time or it's energy divided by time, depending on the context. So I'll let you do some practice questions. You can turn that in to get some feedback, but otherwise you've got a problem set to do.